Good evening, everyone. Very warm welcome to our 12th Astro-Chat. My name is Professor Andrei Zvelindovsky. I'm head of School of Mathematics and Physics at the University of Lincoln. And I'm very pleased to meet our distinguished guest, Professor Don Kurtz. Hello, Don.
Hello, Andrei.
With help of internet, we can meet and chat about various astrophysics things. Don is physically now in South Africa, and I'm in England. We have lots of our regular visitors. I see in the chat people as far as I see from California to Skegness joining us in this discussion. But there are all these new visitors, so I just say a very few words about Don, who is originally from San Diego in California, where he obtained his bachelor degree from San Diego State University, which followed with a doctorate degree in Texas in Austin. And after a postdoctoral position, Don spent about a quarter of a century working in South Africa, where he is also right now. After that, it was another about a quarter of a century here in the United Kingdom, in the University of Central Lancashire. Right now, Don is a Professor Emeritus from University of Central Lancashire, also distinguished professor in Northwest University in South Africa, where he's now, and we're very pleased to have Don also as a visiting professor in the University of Lincoln in the United Kingdom. Don has a longer distinguished career in astrophysics, has over 1,500 of scientific publications, about 2,000 of nights and telescope. He is author of 866 pages classical nowadays textbook in astroseismology. He also served as vice president of Royal Astronomical Society. He gave public talks all over the world. I think just one continent missing. Is it right, Don?
Yes, Antarctica.
Yeah, so one more continent to go. And for his services to astrophysics, he was awarded Royal Society or Royal Astronomical Society Service Award 2022. And with that, I would like to welcome Don here and give floor to you. Don will give a presentation, which then will be followed by a Q&A session. So I invite everyone to post your questions in a live chat just below in YouTube, and we will try to answer as many as we can.
Okay, thank you, Andrei. Good evening, everyone. I'm now going to switch over to my presentation, so bear with me while we get that started. And Andrei, can you confirm that that's showing for me?
Yes, we can see that.
Okay, thank you. Well, everyone, if you think 65 years ago, back in the late 1950s, humans at first escaped from the ground. The Russians put up the first Earth-orbiting satellite, which they called Sputnik, which means traveler. And that was not escape from the Earth's gravity, but at least was off the ground. It was still confined by the Earth's gravity, though, to orbit the Earth. And over the following years, we eventually did escape the Earth's gravity, sending missions out to other planets. And this evening, what we're going to talk about are the two Voyager missions conceived in the 1960s, launched in the 1970s, and they now have escaped not just the Earth's gravity, but they have escaped the sun's gravity too, and they are now out in interstellar space. This evening, I'll tell you the story of their background, something about their accomplishments, and particularly where are they now and how is it we can still talk to them. You'll see from the little bit of the poster that I'm showing at the bottom, experience the charm of gravity assists every 175 years. And so let's look at how that came about. Back in the 1960s, there was a graduate student at Caltech named Gary Flandreau. He's had a very illustrious career in space physics. As you'll see there, he's a chair of excellence in space propulsion at the University of Tennessee now, in his 80s, still working quite nicely. And when he was a student at Caltech, he was set the task and succeeded to look for a way to use the gravity of the planets to give a boost to our satellites, because our problem is in getting satellites to other planets, we have to pay a lot for the fuel and the propulsion to have them climb against the sun's gravitational field. Now, if there are two bodies orbiting each other, like just the Earth around the sun, or just the moon around the Earth, or even just an electron around a proton, like in the hydrogen atom, that's called the two-body problem. And that is mathematically completely solvable. We can figure out everything that is happening and will happen. But as soon as you have three bodies, the problem's more difficult, and you can't just solve the equations. You've got to do more numerical work. And what he discovered in looking at the positions of the planets is there was an opportunity coming up in the 1970s where a satellite launched to Jupiter and Saturn could use the gravity of Jupiter to fling the satellite at no expense to us at a higher speed out to Saturn, and then use the gravity of Saturn to fling it out to Uranus, and then Uranus's gravity to fling it to Neptune, and then Neptune to throw it right out of the solar system. That was the idea. Here's the NASA poster, the Grand Tour. You can find this on the internet, download it for you if you like. It says, once in a lifetime getaway, the Grand Tour, Jupiter, Saturn, Uranus, and Neptune. Once every 175 years, now boarding. NASA initially funded this well, but cutbacks in funding meant that the mission had to be scaled down a bit. And let's look now at what happened. The planning began in the 1960s. The mission was then approved around 1972. 5 years later, the satellites were built, ready to go, and they were launched. Now, Voyager 2 was launched first, 20th of August, 1977. Just a moment, let me get a cursor here so you can see what I'm pointing at. 20th of August, 1977. And then Voyager 1 was launched the next month. Now, why is Voyager 1 launched second? Well, Voyager 1 was on an orbit that took it out to Jupiter and Saturn first. So Voyager 1 got to Jupiter, as you can see here, in March of 1979. And then Voyager 2 following it got there July of 79. And as they passed by Jupiter, they observed the planet, and they in particular observed the moons, made some incredible discoveries. I'll mention those in just a little bit. And then the interaction of the satellite with the gravity of Jupiter and the gravity of the sun, the satellite, by being positioned just right, stole some of Jupiter's energy and marginally, unmeasurably, would have made the giant planet Jupiter move slightly closer to the sun, and the energy that it took from Jupiter flung the satellite out at a higher speed than we could have made it go with our propulsion fuel to fling it out to Saturn. And so Saturn was the next target, and Voyager 1 and 2, you can see, got out here. Voyager 1 to Saturn, November of 1980, and then Voyager 2 not until August of the next year, 9 months later. Now, the original plan was for these two little satellites to last for 4 years to get to Jupiter and Saturn. The idea was that if Voyager 1 completed everything that it was wanted to do when it passed by Jupiter and Saturn, and it was completely successful, then Voyager 2 could be repurposed, and as it passed by Saturn, use Saturn's gravity to fling it out to Uranus and Neptune. If Voyager 1 had failed, then Voyager 2 would not have used that gravity assist and would have not been able to go out to Uranus and Neptune. Both of the satellites were completely successful. And in fact, they were so successful that even though they were designed to last for 4 years, here we are 45 years later, and they're still communicating with us out beyond the solar system in interstellar space. It's a phenomenal success of engineering, planning, astronomy, science, and human achievement. Now, there's to give you some idea what the size of these two little satellites are. There's one of them in the clean room while it's being built, and you can see some of the workers over here in their white suits with their hats on. Of course, try to keep everything completely clean, no dust, and you can see the satellite's a bit bigger than a human. It had a mass of about 720 kilograms. There's a artist's impression. There were 11 different instruments on board, and they had a whole lot of different jobs. Down here was the power supply. Now, just to jump ahead, where the Voyagers are now, the sun is about 25,000 times fainter than it is here at the Earth. You can't use solar power on these satellites. They're too far away, and the sun's just not bright enough. And so they're powered by radioactivity. They've got a small nuclear reactor on them. It's plutonium oxide, and as it decays, it produces heat, and the heat's used to generate electricity in this little power system right here. And that's still working 45 years later. One of the main instruments up here is the camera, the imaging cameras, and we'll see some pictures that those took. And then very importantly, this boom right here was to measure magnetic fields, and that was one of the important missions of both satellites. Over here in the artist's impression in space, there's the boom for measuring magnetic fields sticking out off the satellite. This radio telescope dish you see on there is the way it communicates with us. And we will come back to that communication right near the end of the talk before I take questions. And I think you will be astounded with the incredible ability of the people who designed this and the people on the ground to continue having this little satellite communicate with the Earth now where it is tens of billions of kilometers away. This I downloaded today. You can go on the Voyager website and see exactly where it is now. This was a few hours ago when I downloaded this. The mission now, Voyager 1, is 45 years, 1 month, 22 days, and now more than 23 hours because this is a few hours ago I downloaded it into its mission. 45 years these have been going, not the 4 years that was planned. Distance from Earth, well, in miles, 15 million miles. That's up 15 billion miles, 24 billion kilometers. And Voyager 1 is now moving at 38,000 miles per hour. And to try to put that in perspective for you, since those satellites have left the solar system and they're headed out to the stars, if they had been aimed at the nearest star, Proxima Centauri, they're not, but if they had been aimed at that star, at the speed they're moving now, 74,000 years to the nearest star. It really gives you the idea how far it is to the stars and how difficult it is to go out and travel between the stars. 74,000 years to the nearest star with the fastest satellites we've ever sent out of the solar system. There was our first remarkable view of Jupiter when the Voyagers passed by Jupiter back in 1980. So there's a Voyager picture. Now, we've got better pictures now. We've got Juno orbiting Jupiter right now. We're getting spectacular pictures from that. But these were a revelation when they came out back in 1980. This picture you're looking at now, Jupiter is 11 times bigger in diameter than the Earth. It's 330 times the Earth's mass, and it's entirely gaseous. Hydrogen and helium, methane and ammonia. And here in the atmosphere, where the winds blow 400 kilometers an hour in these bands that you see, this is a hurricane or a cyclone that we've been watching through telescopes for 3 centuries now. It may have been blowing a lot longer, and it's bigger than the planet Earth. And there was our first really great view of that. You can see it with a small telescope from the Earth, but in nothing like the detail that we can see in that Voyager picture. Voyager then went up, Voyager also imaged the moons of Jupiter, and we'll see that in a little movie I'm going to show you in a moment. It saw volcanoes erupting for the first time on the moon Io, live volcanoes going off on a moon around another planet. It found cracked ice and the evidence for oceans in Europa where we think there may be life. And you'll see just a little bit more of that in a moment with the NASA movie. Beyond Jupiter out to Saturn, spectacular views of Saturn's rings, which are made up of millions and millions of small moons, all orbiting about Saturn. Voyager discovered that there were tiny moons, some tens of kilometers across, which were shepherding the particles inside Saturn's rings and producing some very interesting effects that we hadn't understood up to that point. And importantly, Voyager 1 flew by Saturn's giant moon Titan. Titan's a little bit bigger than the planet Mercury. It's got a thick atmosphere, even thicker than the Earth's atmosphere. And with Voyager flying by Titan and getting a good look at it, that then made plans for the later Cassini mission, which sent a lander down into the atmosphere of Titan and eventually down onto the surface. It didn't last very long under the high pressure and the incredibly cold conditions, but showed us the surface of Titan. And Titan's got liquid on it. It has lakes and rivers, but the lakes and rivers on Titan are made of ethane and methane, of hydrocarbons, not water like here on the Earth. Then with the success of Voyager 1, when Voyager 2 came by Saturn, it was able to be repositioned so that the gravity of Saturn flung it out to Uranus. Uranus turned out to be pretty plain looking, looking at it face on, but here's a look that we could never see from the ground. As Voyager 2 passed by Uranus, it turned around and to look back at it towards the direction of the sun. And so this is the side of these outer planets we could never see from the Earth. We only see the sunlit side because they're so far away. And there's the dark side of Uranus with just a sliver of a crescent Uranus showing with the look back from Voyager 2. The gravity of Uranus then flung Voyager out to Neptune. But as it passed by Uranus, it took a picture of the most remarkable little moon. This little moon is named Miranda. It was only discovered in 1948. It's a little bit smaller than 500 kilometers in diameter. And you may remember from The Tempest, Shakespeare's The Tempest, Miranda, main character, this young girl who's never seen anyone except for her father and the rather deformed Caliban, and of course the spirit Ariel. But she's lived her whole life on an island with no contact with other humans. And a shipwreck brings a bunch of young men. And when she sees them, she says, "Oh, brave new world that has such people in it." And Miranda's a brave new world. It was smashed by something that almost tore it to bits. It fell back together. But what you're looking at right here is the biggest cliff in the solar system. If you can see my cursor in the lower right, that ice cliff is 20 kilometers high. It's more than twice the height of Mount Everest, straight up. Now, if you're a climber, and you might like ice climbing, people do, there's the greatest ice climb in the solar system. And because the gravity of Miranda is so small, if you were climbing on that ice and you slipped and fell, if you fell a kilometer and landed on a ledge, you wouldn't hurt yourself. If you fell the whole 20 kilometers, you're in trouble. So there's the miraculous moon Miranda, imaged by Voyager 2 as it flew by Uranus to be flung out to the planet Neptune. And it got to Neptune and discovered Neptune has got weather. Now, Neptune and Uranus are about 4 times the size of the Earth, and they're also gaseous planets, no solid surface. But there on Neptune is what's called the Great Dark Spot. And remarkably, it's at the same southern latitude, 21 degrees south, as that Great Red Spot on Jupiter. And we've been watching that Great Red Spot, that hurricane blow on Jupiter, for 3 centuries. We figured that this Great Dark Spot would be permanent too. But with the Hubble telescope, we can still see Neptune, and the Great Dark Spot has disappeared. It's gone. We don't understand the weather on these planets well enough to understand why. These white things you see here are very high cirrus clouds, ice clouds probably of ammonia, high in the gaseous atmosphere of Neptune. And then as Voyager went by Neptune, it was doing so well, it actually passed over the North Pole of Neptune 12 years after it left the Earth, and it was within 1 second of being where it was planned to be when it was launched. The people who calculate these orbits are absolutely fantastic at getting things right. And that allowed it to be diverted to go by the little Neptunian moon called Triton. Triton has very probably been captured by Neptune. It orbits the wrong way around Neptune. It probably came from what we call the Kuiper Belt in the outer solar system, as did Pluto, which used to be a planet, now a dwarf planet. Triton's only 1,200 kilometers across. It's smaller than the Earth's moon, but with this view from Voyager, down here in the summer hemisphere, it warms up to minus 235 degrees Celsius. It warms up to minus 235. The ice is made of nitrogen. Now, nitrogen's mostly what you're breathing. 78% of our atmosphere is nitrogen. And on Triton in the winter, up here, the nitrogen freezes and falls to the ground as snow. But when the summer comes, there's enough heat to cause the nitrogen to sublimate, go from solid to gaseous immediately, and produce what we would call in English geysers, for you in California, geysers, where nitrogen's being blown out under the surface, it's carrying contaminants with it, and the wind's blowing, and you can see these black streaks. The nitrogen then travels to the other hemisphere where it falls again as snow. Now, the time it takes Neptune to orbit the sun's 165 years. And so the time from summer to winter on Triton is a little over 80 years. For those of you who are young enough or ambitious enough, if you come back in 80 years, I predict that this hemisphere up here will have this sort of terrain, and that hemisphere down there will have the frozen nitrogen snow. So with that, Voyager 2 was flung out past Neptune and was heading out of the solar system. As it was doing so, it turned around and it looked back towards the sun. These streaks you see are reflections in the camera, but that little blue dot right there is the Earth. That's the Earth as seen from Neptune. That's one of the most remarkable pictures that's ever been taken in astronomy, and it really puts into perspective how small our planet is that sustains us and sustains all life that we know so far. That little pale blue dot, as imaged by the Voyager satellite way back in 1990. Now back to the sun. This is a movie. It's a time-lapse movie taken by an instrument called LASCO, which is on a satellite called SOHO, the Solar and Heliospheric Observatory, which orbits between the Earth and the sun. It's been up for decades. And what we're going to look at now is what the sun does sped up. Now, down in the middle here is an ultraviolet picture of the sun. That's been superimposed onto this slide. The black circle is a disk in the LASCO telescope that blocks out the sun itself, so we're not being blinded by the sun. And what you're looking at here is first a close-up camera and then a wider field camera of flares and coronal mass ejections on the sun, and these streaks are what are called the solar wind. The sun has a wind blowing off of it at 400 to 1,000 kilometers per second all the time, and occasionally it'll have a giant flare or a coronal mass ejection which blasts off the surface. Now, back in October of 2003, over the following Halloween, there was a massive ejection from the sun. It blasted the Earth, and you're going to see that in just a moment. When that blasts the Earth, it completely whites out your screen. Those are high-energy protons smacking into the SOHO satellite. And if any astronauts had been out on their way to the moon at that point, they would have been killed dead instantly. We're protected on the Earth by the Earth's magnetic field. As we watch this movie, you will see that the stars are moving. That's because the sun is orbiting. The Earth is orbiting the sun, so we're seeing the stars move in the background. And you'll also see Mercury moving in the opposite direction. Now, if you look at the time in the bottom, you'll see how much this is sped up. But you'll just see this continuous wind from the sun. There comes Mercury off the edge. The reason it's got a little arm on it there is it's so bright that the electrons are spilling down on the detector. And there's the proton storm that would have killed the astronauts. So the sun has a wind, and that wind blows out to somewhere. It's an interesting question, how far does it blow? And the Voyagers have answered that. In August of 2012, Voyager 1 left the influence of the sun and the solar wind and went into interstellar space. And then in 2018, Voyager 2 followed it into interstellar space, where the wind from the sun stops and is then affected by the wind from the stars and the gas between the stars. And we're going to watch a little bit of a NASA movie here, and I'll come back to talking to you after we hear what they've got to say.
We have ignition, and we have liftoff of the Titan Centaur carrying the first of two Voyager spacecraft to extend man's steps farther into the solar system than ever before.
They were launched in 1977. That's a long time ago. We say 41 years, but it's really two generations ago. You can think of what the technology was. Your smartphone has 200,000 times more memory than what the Voyager spacecraft have. And so it's just exciting that we've been able to get it into interstellar space.
We launched two Voyager spacecraft. They were basically the same, but they were on different paths. Voyager 2 was the one that was chosen to do the grand tour. That is to fly by Jupiter, and then Saturn, and then Uranus, and then Neptune. And then after 1989, we began what is now called the Voyager interstellar mission. We were on a path we hoped to get to reach interstellar space while we still had power on the spacecraft to transmit the data back. And that's what Voyager 1 did in 2012, and that's now what Voyager 2 is starting to do in 2018. The sun creates this huge bubble or plasma, ionized material, goes outward at 1,000,000 miles per hour and creates a bubble. And inside the bubble, most of the material has come from our sun. The magnetic field has come from our sun. Outside the bubble, most of the material comes from other stars that exploded 5, 10, 15 million years ago. We have an instrument which measures the wind coming from the sun, and we saw that, in fact, there was no longer any measurable solar wind. We had left the bubble, basically.
The team has been looking forward for this for a long time and really working hard in an engineering sense to make this day happen and to keep the spacecraft with all the instruments on so that they could, all 5 instruments could sense the heliopause crossing and have data for that. What that means is that the Voyager 2 spacecraft is now traveling in interstellar space.
Well, this is just contributes to the number of discoveries that Voyager has been making. And this is one we'd hoped we would have the chance to do. Unfortunately, the SPOS spacecraft were still operating when they reached interstellar space. It's really quite remarkable. Voyager changed our view of the solar system, really. I mean, we saw these active volcanic activity on Io. We saw the possibility of ocean on Europa. Just time after time, we were discovering things that we had not really even imagined some years before the Voyager mission. What makes it so exciting is not only do we confirm what we thought we knew, but even better, it tells us where we didn't know that there was something to be discovered.
Well, the man you were just looking at was Ed Stone, who is the principal investigator on the Voyager mission. He started that in 1972. And here's Ed Stone back when he was just beginning as the principal investigator on the Voyager mission. Here he is 30 years into the mission, getting an award from Nichelle, 30 years of accomplishment. If you don't recognize her there, you may recognize her as Lieutenant Uhura from Star Trek back in the 1960s. And then 45 years later, just 3 days ago, Ed Stone's retired after 50 years as the project scientist on Voyager. Just 3 days ago. What an incredible career. Now, along the way, for 10 years, he was the director of the Jet Propulsion Laboratory. He's won just about every award going, so he's had a very illustrious career, very accomplished. Susie Dodd is still the project manager. She joined the mission when it was at Jupiter and Saturn. She then moved off to work on Cassini orbiting Saturn, but came back for the interstellar mission and is with the mission now. There's an artist's impression of that solar bubble coming from the sun's wind, and then the 2 satellites having moved out into interstellar space where they're out amongst the stars and the gas from the stars. Now, to communicate with this thing, here is the phenomenal information. To talk to it now, which they can still do, the data goes up at 16 bits per second. When the satellite responds, it can send data down at 160 bits per second. This talk that I'm giving you right now is coming off my home broadband, and it's running at 30 million bits per second. Just compare those numbers. This is early 1970s technology. The spacecraft originally could generate about 470 watts with those nuclear reactors. It's down to about 250 watts now. The transmitter with this big dish here takes 22.4 watts to run it. And your phone sends out a signal at 3 watts. So it's a little bit stronger than a phone signal. But at 24 billion kilometers, you're not going to be able to talk to your phone. In order to get information back from this, the NASA uses its deep space network, not just the 70-meter radio dish, but some others added in now. Because when the signal arrives, it's got a power of 10 to the minus 16 watts. That's 100 billionth of a watt. And yet, we can still communicate. It takes 22 hours to send a signal out to it. And then for it to respond takes another 22 hours to come back, but it is still talking to us. Now, on board, both of the Voyagers are what are called the Golden Records. Those were designed by Carl Sagan, his wife, Andrew Yan, others who were involved. And on those records were put the voices of 55 different languages here on the Earth, a great deal of music from all different countries across the world, and an explanation of how the record works and where the Earth is. Now, I think for most of you, except for the older amongst you, you probably don't know how a record player works either. So pity the poor alien if some alien ever finds this thing, trying to figure out from this description here how this record and a stylus works and what speed to turn it at. How to tell them what time, how do we measure time? Well, down here in the lower right is a diagram that we hope any intelligent species would recognize as representing the hydrogen atom. In the hydrogen atom, an electron can be either aligned or misaligned with its nucleus, and when it flips from one to the other, it emits radiation at a wavelength of 21 centimeters, and our galaxy is just full of it. And so we know that any intelligent creature would be aware of 21 centimeter radiation. So there's how we're trying to tell them what our time base is. Over here is a map of where the Earth is with respect to 18 pulsars, which are very identifiable from their frequencies. And if this object should ever be found by aliens in the next maybe millions or tens of millions of years, this could pinpoint the Earth. But 100 million years from now, all these stars are moving, and this map's not going to be very good. There's some people who think this was a bad idea, and that if aliens find it, they'll know where to find us. I don't think that's anything to worry about. And so it was fun to put that on there and explain where we are. There were pictures put on it, and here's a list of the sounds that were put on. This may be a bit small for you to read, but volcanoes, earthquakes, wind, surf, crickets, birds, chimpanzee, wild dogs. Down here, life signs, a mother and a child, a train, a horse, a whole variety of earth sounds on it. And then, of course, music from all different cultures all over the world. Now, the Americans put on some rock and roll music. This was 1970s when this was planned. And in 1989, when Voyager passed by Neptune and that little moon Triton, there was a big party at JPL, and invited to play at the party was a musician. Some of you might recognize there, Chuck Berry, because his song, Johnny Be Good, is the American piece of music on the golden record. There's Carl Sagan, the astronomer who did Cosmos, wrote many books, presenting Chuck Berry with an award at the time of the 1989 flyby past Neptune. Sagan said of this, the spacecraft will be encountered and the record played only if there's advanced spacefaring civilizations in interstellar space. He really didn't think that's ever going to happen. I don't either. Space is big. But he says the launching of the bottle into the cosmic ocean says something very hopeful about life on this planet. It's absolutely amazing that we've had the ability and the technology to have sent an object out of our entire solar system, out to wander through the galaxy, through the stars. So thank you for your attention this evening, and let's switch over to question time. And I think I've stopped sharing, haven't I, Andrei?
Yes.
Okay.
Thank you very much, Don, for this very, very illuminating presentation. I kind of I remember the basic Voyagers since I was a small kid, so they've been kind of largest part of my life, at least the one I kind of maybe was interested a little bit in scientific things. So, and they still there, and they still communicate with us. So it is really, really special. And with that, we turn to the questions. I see questions start to arrive. And I see for John Levenhall ask, how is that the satellite signal never wavers such that the signal can be received complete? What is it sending today?
John, I'm not sure I understood your question, why it should waver. The satellite is sending out a signal using radio waves. And because the space between the satellite and the Earth is essentially empty, there's nothing to impede those radio waves, and they come to us. Of course, it's extremely important that that dish on the satellite be pointed exactly at the Earth. And there is still some propellant on the satellite to keep control so it can keep pointing at the Earth. And that's what some of the signals that go up to the satellite tell it to do. Keep pointing at it so we can talk to it. But the radio waves travel through essentially empty space without being impeded at all. They travel at the speed of light, and they come to us from the satellite to the Earth. So there's no wavering of that. It's a clear signal.
John, then it's a bit of extra. When will it get too faint to receive?
Thank you, John. That's a good question. The operators, Susie Dodd, the project manager there, are not sure. They think 2025 maybe, but some hope 2030 or even a bit longer. But it's getting to the point now where not too many more years, and it will no longer be able to communicate with us. That'll be a sad day. I hope it makes 50.
Yeah, so it kind of answers question of Charles Toddy, who says how much longer Voyager team expect keep communicating with satellite. And then there is question from group IMP64. Thank you. Roughly speaking, in what direction the Voyager's traveling? Towards the center of our galaxy, into our spiral arm, towards the edge of our galaxy? I've always wondered. Thank you.
Okay, thank you, group, whatever your number was. It will be in our spiral arm, although it's moving at 38,000 kilometers per hour, which is, just a moment. Well, that was 38,000 miles per hour on that slide, wasn't it? Let me put that in kilometers per hour. It's moving at about 15, 16 kilometers per second with respect to the sun. And that's roughly the sun's speed as it orbits about the center of the galaxy too. So this thing does not have the speed to, and it doesn't have the energy to get out of the galaxy. So we got to the point where we've made something escape the sun, but it certainly is not going to escape the galaxy. And if we wanted to send it to the outer galaxy or into the inner galaxy, that would cost a lot of energy. Basically, it's going to orbit around the center of the galaxy, much as the sun does. It'll be separate from the sun. And just as the sun does, it will take about 200 million years for each orbit about the center of the galaxy.
Thank you, Don. And just if I add from myself, how far orbits of both Voyagers kind of go apart as they move?
Oh, you mean how far apart are they from each other, Andrei?
I mean, yeah, they kind of, will they go to very kind of different orbits around center eventually?
Yes, they've gone their separate ways. When Voyager 1 passed by Saturn, because of its visit to Titan, it actually was ejected from the plane of the Earth's orbit around the sun, and it was sent up in a more vertical direction out of the plane of the orbit, whereas Voyager 2 stayed in the plane so it could go to Uranus and Neptune, and then it even stayed in the plane. And so they're on very divergent orbits. Both of those, they don't have the speeds to move very far away from the plane or in the galaxy, but they will go their separate ways. They're not going to stay together. And if you would like to come back in a few billion years' time, they'll be nowhere near each other.
Yes, probably I will try. There is a question from Anthony Blockham. Are the Voyagers expected to ever fly by any other significant galactic landmarks on their remaining outward journey?
Okay, Anthony, the answer is no. They are not yet at what we think is the inner edge of the Oort cloud, where we think comets come from. But comets are tiny, and the satellites are tiny, and we don't expect them actually to interact with a comet. They passed out through the asteroid belt as they went from Mars to Jupiter, and many satellites have done that. There's never been a collision. That's mostly empty space out there. And we don't expect those satellites to interact with anything more in the solar system. And then when they get out between the stars, oh gosh, no, the stars are so far apart. Let me put that in perspective. I'm going to shrink down my head to the size of, I'm going to shrink the sun to the size of my head, and I'm going to shrink the next nearest star to the size of Andrei's head. Now, we're a little bit too far apart being in South Africa and being in England, but on that scale, if I shrink the two nearest stars, the Sun and Proxima Centauri, down to the size of our heads, then the distance between us is on the order of maybe 4,000 kilometers. It's really empty space out there, and it's extremely unlikely that these objects are ever going to encounter another star. Just think of it, the sun's been orbiting the galaxy for 4.6 billion years, and it's never run into another star or come close to one. Stars are too far apart.
Thank you, Don. Then a question from Michael Wyman. Please, would you explain how gravity assist works?
Yes, Michael. I actually have a slide I could show for that, and I wonder if, I think a lot of you are going to have that question. Let me see if I can give you an analogy. I'm going to pop back to my screen share. So just bear with me for a moment. And the reason this wasn't in initially is that, you know, to give you question time, I sometimes run out of time. Can we see the slide now of this train?
Yes.
So this is an analogy of how you get a gravity assist. I'll come back to gravity in a moment, Michael, but here's a little boy. You see the beanie he's got on his head with a little rotor spinning on it. So it's obviously a little American boy. And he's throwing a ball at a train. He throws the ball at 30 miles per hour. The train's coming at him at 50 miles an hour. And we're going to assume when the ball hits the front of the train and bounces, it doesn't lose any energy. It's what we call an elastic collision. Well, from the train driver's point of view, that ball's coming at him at 80 miles per hour. And so when it bounces off the train, it bounces off the train at 80 miles an hour with respect to the train, but the train's going 50 miles an hour. And so now the ball is up to 130 miles an hour compared to the 30 miles an hour that the little boy threw it at. So there's a speed assist. And now I'm trying to get back. All right, I'm back. There's a speed assist in a simpler form. In the case of a gravity assist, a satellite, we do this with the Earth. We've sent satellites out which go out into the solar system, but not very far, and then they fall back and they come close to the Earth. And as they pass close to the Earth, if we position them just right, so the Earth and the Sun are in the right position, as they swing by, the interaction of the three bodies. You'll remember I told you this three-body problem's complicated. You can't just write down an equation and solve it. As the three bodies interact, the satellite robs some energy from the Earth, and that then flings it out at higher speed. But then the Earth has lost a little tiny bit of energy, and that makes it move slightly closer to the Sun, but immeasurably so as far as we're concerned, because the satellite's so tiny compared to the Earth.
Thank you, Don. John Levenhall still asks, what data is it sending back nowadays?
Oh, it's sending data from the... Thank you, John. That's a very good question. Because it has so little energy now, it's down to only 240 watts, it's had to turn some of its instruments off. And so the cameras are turned off. Cameras are turned off because there's nothing left to take any pictures of. It's out there all by itself. The magnetometer, the thing that measures the magnetic field, one of the more important instruments, is still going full speed. And that measuring the magnetic field from the Sun and now interstellar space is part of the way of knowing that the satellite's in interstellar space. The particle detectors that could measure the solar wind and are now measuring the wind from the stars, those are still operational. And so a couple of those 11 instruments are still operational, but quite a few of them have had to been shut down because there isn't the energy to run them anymore, because that nuclear reactor is not producing as much energy. And it's possible that the energy will drop to the point that before we lose contact, before it can no longer talk to us, it may not have the energy to run any more science. And so at that point, it still will be able to look back at us and we'll say goodbye to each other.
Thank you, Don. Thank you. It actually answers several other questions where people were asking if it's transmitting pictures from Janet Mary Nixon. So yeah, definitely no pictures anymore. Or there is somebody with Nick Aviator. If there are any optical instruments still functioning. So yeah, so
all the cameras are shut down.
Yeah, and then there is a question from Minerva Bird. Don, what music would you have put on the Voyager rocket?
Minerva, that question, I think you're asking what would I personally put on, but I could also try to answer what else was on there. Now, this is a bit like Desert Island Discs, isn't it? Would I have chosen Chuck Berry's Johnny B. Good? This is now, I have to think of what I would have chosen back in before 1977. A piece of rock and roll is an American piece of music, sounds good. I would certainly like to see In the Western tradition, some classical music, and the German music that's on there is one of the Brandenburg concertos by Bach. But there is music from Mongolia and from Southeast Asia and from Africa and panpipes from South America. And now that I think of that, I certainly would like to hear some Peruvian panpipes on there. So let me just say that for any of you who would like to, if you look up Golden Record, Voyager, you can actually download the whole thing and you can look at the pictures and you can listen to the music. It's available.
Thank you, Don. And Minerva tells Don's desert island discs indeed. And just from me, which committee or group were choosing the music for the Voyagers?
Oh, do you know, I don't know who the whole committee was, but I know that Carl Sagan and Andrew Yan, who at that time were not married, but were already a couple, they certainly were very involved with the Golden Disc, but there were lots of other people involved too, and I don't know what the names of the other people involved are. But again, if you look up Golden Disc, Voyager, all of that information is both widely available and widely discussed, and lots of people still like to listen to that disc.
Thank you, Don. There is a question from Sean Shields. Would it be viable to launch a chasing relay satellite to keep the contact for longer?
Sean, the answer is yes, it would be possible. But the answer is no, it won't happen, because that would be expensive. And the science that the Voyager's done is it had a 4-year mission, and 45 years later, it has really completed the mission. And the money that it would cost to chase it, still talk to it, would be much more interesting to spend on one of the many, many, many proposed missions that are not funded yet to do new science. NASA, ESA, the Chinese Space Agency, Russian Space Agency, all these space agencies get many, many more proposals of fantastic science than there is money to fund them. And it's fantastic that NASA even agrees to continue spending the money to continue talking to Voyager, because when the data comes down, they have to use their deep space network. They have to use some of the biggest radio communication dishes they've got on the ground for talking to satellites and lock them up for a while talking to Voyager. And that needs a lot of people too who've got salaries. And it's always the case when missions almost always outlast what they're planned for. And then to talk NASA, in the case of the American space, or ESA, to talk them out of more money to keep your mission going when somebody else wants that money for their new mission, that's a battle that gets fought every year, and it's in review with committees, and that decision has to be taken, and it's always a hard decision.
Thank you, Don. This question from Andy Edgar. Have the probes suffered any damage during the flight?
Annie, so far as we know, nothing significant. They are shielded from in the direction they're going. They're shielded so that small particles bumping into them, there's a particle shield. And they haven't been hit by anything that either penetrated that or caused any problem. But if we could get that shield back and look at it, it very probably would be pocked with little tiny pits from little things that it's hit. It was the case with Voyager 1 that there was a time it was thought that it actually wasn't following its orbit and that it was not in the position we thought it should be in. And it was seriously being considered if that was new evidence for a fifth force and that the law of gravity was not working at the distance of beyond Neptune. That's a really interesting question, because if the law of gravity is not exactly what we think, that may be the telling answer to problems of dark matter and dark energy. So that was very exciting and very seriously looked at. And it turned out the answer was that the heating from the generator and the asymmetrical heat on the satellite actually was generating enough to push it slightly different from a purely ballistical orbit. And we've decided there isn't some fifth force or that gravity's not wrong. That wasn't the problem. But that tracking of it, that was a very interesting problem for a while with Voyager 1 a decade or so ago.
Thank you. Thank you.
Did I answer that question? I got off track.
I think it was, yes. Yeah, I think what answer what was asked. Yeah. Then There is question from a person. Yes, Andy says yes. Thank you. So Marianne Christine 55 or something like this. Are the data transmitted continuously or in batches?
Oh no, Marianne, they're broadcast in batches. And I can't answer right now if you're about to ask me how much time is between the batches, but that deep space network cannot be continuously trained on Voyager. It has other jobs to do. And so there are data dumps. And you'll realize from that 160 bits per second, I don't know how long those data dumps last, but it can't send very much data down, but it only needs to send down the measurements. What's the magnetic field and what's the particle rate? And so we could both go look this up. I don't know the answer to this one, how often those data dumps come, but they're only occasional.
Thank you, Don. Just a bit of question for me. You mentioned this two-body problem, which I just actually explained to my students 2 days ago. And of course, a three-body problem is far more complex. And here we have more complicated, many planets on the way. How difficult was this task of calculating orbit of these satellites, their pathway? Can you just say anything about that?
Yes, Gary Flandre, who did that as a graduate student, was the first one ever to do that. It was very difficult. There were people who preceded him who were developing the techniques, but he had to sit and look at lots and lots and lots of possibilities. He couldn't just do the calculation and say, here's the orbit. And so it could be narrowed down. The computer he was using, they used punch cards. It was incredibly slow. This is a very tedious, long task. But he knew how to narrow it down and to guide it. And he found this remarkable possibility that was just coming up. And of course, if we'd missed it nearly 2 centuries before the next chance to use that gravity assist for those 4 outer planets. Now, you were talking about the multi-body problem, Andrei, and so let me just digress slightly. But here in our solar system, if you look at the Earth's orbit, the Earth does not orbit the sun on an ellipse. All you astronomy students out there, you've learned the Earth's on an elliptical orbit. That would only be true if it was just the Earth and just the sun. But the Earth's being tugged about by the moon and it wiggles back and forth. It's being pulled about by all the other planets. We can measure the distance to the sun to a precision of 3 meters. And at that precision, the Earth is being tugged about by the asteroids in the asteroid belt. It never gets back to the same place it came from. And the big problem is, what if there's an asteroid coming towards the Earth and we don't know if it's going to hit, if it will hit? Why can't we predict that in 2071 that asteroid will hit the Earth? And the answer is, in 50 years, we can't tell exactly where that asteroid will be, because this is a multi-body problem with all sorts of different bodies in the solar system tugging on that asteroid, and we cannot predict its orbit exactly 50 years into the future. That's why we have to keep watching for those dangerous asteroids. We don't know exactly what they're going to do in 50 or 100 years' time.
Thank you, Don, for this. And now I see a question from Charles Toddy. I'm intrigued about the courses the 2 Voyagers took after launch. If 2 was launched first, but 1 go to target first, where did 2 go when that lag behind?
2 could hang around orbiting the Earth for a little while before it was taken out of Earth orbit. When we send satellites out in the solar system to other planets, they're first launched into low Earth orbit. And there they just go round and round the Earth. And then when they're in exactly the right position, the Earth's in the right position, the planet's in the right position, we then fire their rockets and lift them away from the Earth's gravity to take them farther out in the solar system. And so Voyager 2 was parked, orbiting the Earth, until it was time for it to go to get the timing right between the 2.
Thank you.
Voyager 1 was called Voyager 1 because it was going to get to Jupiter first, not because it was launched off the Earth first.
Thank you, Don. Then there was actually a question related to your previous answer from John Leventhal again. Doesn't it wobble on its orbit at all?
John, what doesn't want a wobble?
doesn't wobble on its orbit
So are
at
we
all.
talking about Voyager wobbling?
Yeah, Voyagers, yes.
Yeah, yes, Voyager is still tugged about by the outer planets, but that we can largely calculate with multi-body problem. And so when I said Voyager 1 wasn't quite where we expected it to be, the expectation had to include all the tugging from all the planets that we know. And one solution could be, if it's not exactly where it should be, is not that gravity's wrong, but that there's something out there that we didn't see. And of course, if I can backtrack, the discovery of Neptune was predicted because Uranus had a wobble back in the 1800s, which couldn't be explained unless there was another body. And a couple of astronomers, including the young John Couch Adams in England at the age of 22, calculated where and how big the planet had to be that was tugging Uranus about. And that's where it was discovered. And so, yes, it would have wobbles caused by the other objects in the outer solar system. They're small, but they're measurable. And the telemetry from the satellite, that can be done.
Thank you, Don. Question from DC. Does New Horizon have a detector to test for interstellar space?
Oh, DC, what a nice question. New Horizon was a satellite that went out to Pluto. And it went by Pluto and took pictures of it. And it's now out in the Kuiper Belt. And it's actually been remissioned or repositioned to get some information on some of the objects in the Kuiper Belt. I don't know ultimately where it's headed for, but I think it's still capable of doing photography and taking pictures of things as it passes out through the orbit of these icy bodies from which Pluto and Triton came from.
Thank you, Don. Now a question from Michael Wyman. What has been learned about interstellar space?
Oh, you mean from the Voyagers? We know a lot about interstellar space otherwise, and I don't know that there's any new information about interstellar space from the Voyagers. We do know they are in interstellar space, but we have got very good observations of interstellar space. And, I can't actually answer that if there was some new science discovered about the wind from the stars, out between the stars from the Voyager missions. But since you've asked me that, I'll go do some homework after this talk's over.
Thank you very much, Don. I think we answered. Several people were asking if was any damage to the probes, and I think nothing but what was. Yeah. So, and I see that we basically arrive at our time allocated for this talk. I would like to thank again Don for this illuminating talk as always, and I'd like to thank all the visitors to our Astro-Chat. This is our 12th already Astro-Chat with Don, and we hope to meet all of you and Don here again in this virtual space and talk about another exciting Astro events. Thank you all very much.
Okay, thank you everybody for coming this evening.